Hello everyone, welcome back to my channel. So in this video we are going to discuss about deadlock avoidance, and in that too we'll discuss about the banker's algorithm. Now we saw in deadlock avoidance that basically deadlock avoidance talks about if a process is requesting for the allocation of a resource to it, we check if the allocation causes a deadlock or not. So that is what we will check in this with the help of banker's algorithm. Now let's say that P3 process requests for 1 0. Here this table has been given where these are the allocated and this is the max that it can have. Now let's check for a few things. First of all, let's check that if we add this P3 to the allocated ones, would we get it more than max or not? If it's more than max, then we can't allocate, but if it's less than that, we can allocate. So if we add 1 0 to 1 1, it would become 2 1, and that's valid because we have max 2 2. Now let's check the total number of resources available. Now we can see that total R0 allocated is 2 plus 3 plus 1, which means it's 6, and 10 is the total, so available would be 10 minus 6, which means 4. Then here we have 2 R1s allocated and total we had 5, so that would be 5 minus 2 3. Now if it's available, if the resource allocation request is more than the available, then also we'll stop it, but here we can see that it's not more than available, it's sufficient, so we can allocate it. And then we'll also see that if it was satisfying this earlier condition, that if it's under max, but even if it's out of available, then we would have not allocated it. Now comes the major part of this algorithm that we need to understand clearly. Now let me write the code for this. So this is the code. Now what we basically need to do is that we need to check that if we allocate what resources the particular process is asking for, do we get a safe sequence or not? If we get a safe sequence, then it means that we can allocate it, and if not, then we cannot. Now, so for this, what all things we need to check would be something like this. First of all, we need to create a need row here. Now allocated was how much resources are allocated to each of these processes, and max was how much max are these processes allowed to take. Now we'll calculate this need, but before that, first of all, since P3 asked for 1 0, so we'll update this allocated one. So what will it become? So it will become 2 1 after this because 1 0 has been added. Now after this, what we do in need matrix is that we calculate the number of resources that we can have. Like from here we'll get 7 minus 0 7, 5 minus 1 4. Now then we'll have 3 minus 2 1 and 2 minus 0 2. Then here we'll have 9 minus 3 6 and 0 minus 0 0. Then 2 minus 2 will be 0 and 2 minus 1 would be 1, and here 4 and 3. So this is the need row here. Now let's see what this code says. So while all P's are not added to the safe sequence, find a PI such that need I is less than equal to available I. So now in the previous section we saw that available was equal to 4 3, but since we allocated 1 0, so now it becomes 3 3. If we'll calculate it from here, we'll get it 3 3. We can calculate it like this is 10, then now since we've allocated 1 more here, so 2 3 2 becomes 7. So 10 minus 7 becomes 3. So 3 3 we have available. Now let's check. So if we start checking from the first one, that is the first one from here. So when we check for P0, we'll see that it's not less than equal to available because this is 7 which is greater than 3 and this is 4 which is also greater than 3. So the first pi that we will see would be p1, because 1 is less than equal to 3 and 2 is less than equal to 3. That is 1 is less than 3 and 2 is less than 3. So this condition is satisfied. So if that is satisfied, what we do is we add the allocated I of p1 to available. So what it will become, so this 2 and this 0 would be added, so this will become now 5 3, and our save sequence will have p1 first. Then now our available is 5 3, so we'll go on checking again. So next we'll reach p2, so we'll see that it's 6 0, so that's not a valid one. Then we'll reach p3 and we'll see that this is 0 1, which is less than available, so which means we can do this again. So we'll add this and this, so it will become 7 4. This will become 7 4, and we will add p3 here. Next, let's move on. So we'll see that p4 is also valid, because 4 is less than 7 and 3 is less than 4. So, and since it's 0 0, so even on adding we'll get 7 4. So p4 gets added to the sequence now. Then we'll come to p0 and we'll see that it's exactly the same. So 7 4. So it's equal to available. So we can add this also. So p0 gets added, and p0's allocated will also add. So this is 0 and this is 1. So this gets added and this will get updated. And it will become 7 5. Finally, then we have only one p left, which is p2. So we'll see that the need is less. So that will it's less than available. So okay, this is available, not available I. So we can add p2 also to the save sequence, and then we'll add this, and this will become again 10 5. So this means that we have a save sequence ready. Now since we can develop a save sequence, it means we are allowed to allocate what p3 requested for. That is for which we were running this algo. So p3 requested for 1 0. So we can allocate this. Now we need to discuss a bit of something about Banker's algorithm here. So first of all, let us understand the limitations as to why it's not a totally practical approach. So first of all, we say that we should know that what each process needs resources. Like we are telling in advance that yes, this process would need these resources and it would require this much. So that's not actually possible. That's not practically possible. So that is one limitation. And we also consider that once this process is done, it releases all its resources. That is why we were adding it to the available one. So since we're adding it to available, it means that this process, once it's done, it releases its resources. That's what basically Banker's algorithm was. So this is also something that's a limitation, that it needs to release the resources when it has already used it. Now let's understand one more thing about safe and unsafe. So there are two parts of this system. That is one where we consider it to be unsafe, and one where we consider it to be safe. And deadlock is not basically this whole segment of unsafe, it's basically a part of it. So if it's in deadlock, it's definitely unsafe, but if it's unsafe, it does not mean that it's because of a deadlock. So deadlock is a part of unsafe and not totally unsafe. And that's it for this video. We'll meet in the next video with a new topic.